This is lecture number 9 in my series on classical thermodynamics. In the previous lectures, we had met the zeroth and the first law of thermodynamics. And the most common form in which the first law of thermodynamics is expressed happens to be Q equals delta U plus W, which has in its heart a conservation of energy statement. Q is the kind of energy which is supplied from the outside to the system through diathermal walls, and part of this energy goes into doing work, W being the work done by the system, and the rest of it goes to increase the internal energy of the system. Of course, the actual statement of the first law, as we saw earlier, did not really involve either internal energy or heat. It actually stated that work done under adiabatic conditions is independent of the path. Using this, we could define the concept of internal energy and then went on to define the concept of heat. For an infinitesimal version, especially for a hydrostatic system, where the only means of doing work is the so-called hydrostatic work, PDV, we have the expression d cross Q, the inexact differential whose integral would give you the amount of heat transferred, is equal to du plus pdv. du, of course, is nothing but the differential of the internal energy, and pdv is the work done by the system when its only means of doing work is hydrostatic expansion. The heat capacity for any system can be defined to be C equals d cross Q dt, the rate at which heat is absorbed for unit rise in temperature. But what is very important is to remember that this depends not only on the system but also on the process. Now, later on we will see that it is actually very, very useful to express the internal energy as a function of three variables: the entropy, the volume, and the number of particles. This is for a hydrostatic system. And of course, we are in no position to say that yet because we have not even introduced entropy, or we have not even gone close to the second law where entropy comes in. But if you were to express U as a function of temperature, volume, and number of particles, keeping the number of particles fixed, as we are doing for the systems that we are talking about, we would get du is del U del T at constant V dt plus del U del V at constant T dV. This again is true for a closed system which can be described entirely in terms of T, V and N, a closed hydrostatic system. Closed here, of course, means that N does not change. Now note that for such a system, if a process takes place at constant volume, pdv term will vanish, so will this term. So del U del T at constant V dt will be the amount of heat absorbed. So d cross Q dt for such a process which occurs in a hydrostatic system under constant volume, will simply be the heat capacity, Cv. So this can also be written down in the form Cv dt plus del U del V at constant T dV. We had also seen, at least at an experimental level, that Joule's experiment told us that for an ideal gas, internal energy depends only on the temperature and not on the volume. So for an ideal gas, this particular term would vanish, and so you will be left with only du equals Cv dt. So this is essentially a recap of whatever we had done earlier. In fact, we had done more, but roughly these are what we are going to need in this lecture and maybe the next lecture. Now, the first new concept that we introduce in this lecture is one of reservoirs. So what exactly is a reservoir? A reservoir actually is an idealized system that we often use when we describe the interactions of a system with its surroundings. A reservoir, or more precisely a thermal reservoir, is a system enclosed by a diathermal wall so that it can be put in thermal contact with other systems, and such a system has a huge heat capacity. Its heat capacity is so immense that its temperature does not change discernibly despite exchange of heat with the surrounding system. So whatever system is brought in contact with a thermal reservoir will either receive heat from it or release heat to it depending on the temperature difference. But no matter what happens, the temperature of the reservoir itself will not change. So although T, or strictly speaking theta, the empirical temperature, is a label for the state of a reservoir, it's really not much used as a label. It essentially helps to distinguish one reservoir from the other and not two states of the same reservoir. Two states of the same reservoir will always have the same value of theta. In fact, the only parameter that can distinguish one state of the reservoir from another is basically its internal energy, U. And as I've noted here, its temperature T or theta as well, but that is rather trivial because that will never change. So, the internal energy of the reservoir is actually an important determinant of its state, and later on we will talk a lot about cyclic processes. Especially, you will see situations where reservoirs are also included within a cyclic process. Now, this can happen only if the reservoir is back to its initial internal energy. And this is going to be very important in the discussion to come. Now that we have talked about cyclic process, let us make a start and talk about a very, very important kind of cyclic process, which is very important both in the development of thermodynamics as well as its major practical application, which helped the science of thermodynamics essentially to create and rule the civilized world. I am talking about something called heat engines. We will now begin our study of heat engines. Rather than follow the usual route of starting with simpler engines and slowly increasing the complexity, I would prefer jumping off the deep end and start with the most general possible engine that we can think about. Basically, the most general engine that we can think about is a system which undergoes a cycle. It returns back to whichever state it started with while interacting with several reservoirs, R1, R2, R3, Rn plus 1, etc. Each of these reservoirs will be at temperatures θ1 or T1 as the case may be, θ2, θ3, θn plus 1 and so on. And what this system is going to do is that it's going to absorb a heat Qn from the reservoir Rn. Of course, this goes for each and every n. And at the end of the day, what it will do is it will produce a net amount of work given by W. Now here, what I have clearly indicated is that the heats are being taken in at different temperatures, and we have used different reservoirs at those temperatures to essentially talk about that. Now, this diagram might make it seem like the heat engine only does work on one single object or gets work done on it by one single object, and that's why we have one work arrow. But that actually is not quite correct. The system could very well do work on several different things or get work done on it by several different things. However, as far as the thermodynamic properties of a heat engine is concerned, the identity of what is being acted upon by the system is really of not much consequence. It may have great practical consequence, but as far as theoretical thermodynamics is concerned, work is work, doesn't matter what it is done on. So I've just lumped together all the possible work arrows depicting works done on individual objects into one single work arrow. As you will soon see, the temperature at which the heat is taken in is going to play a very, very important role in the way the engine performs. And that is why I've decided to break up the amount of heat taken in at different temperatures and indicated their corresponding reservoirs. Now sometimes, in fact, more often than not, in a real engine, heat will be not taken from reservoirs. It will be taken by bodies with finite heat capacity. And as heat is taken in from such a body, the temperature of that body from which heat is being taken will reduce. Or if heat is being rejected to that body, its temperature will increase. Now the way in which we consider such a situation in this picture is that frankly the identity of the particular body from which heat is absorbed is not important. It will turn out that the temperature at which the heat is absorbed is important. So we replace the body by reservoirs. The temperature of the body changes continuously during the process. What we are going to do is we are going to replace it by not a single reservoir, but a continuum of infinitely many reservoirs whose temperatures keep on changing from the desired initial temperature to the final temperature, keeping in mind the exact way in which the temperature of the body exchanging heat with our system had changed. So, we are really not saying that reservoirs are the only things that my engine exchanges heat with. However, replacing whatever the system exchanges heat with a series of reservoirs, maybe a finite number, but very often an infinite number, whose temperature varies continuously, will exactly give me the same basic results in thermodynamics, and using reservoirs will make the theory a lot easier for us to work with. So this is essentially the idea behind the most general heat engines picture that you can see on your screen right now. Let us now turn to what the first law of thermodynamics says about such an engine. Note that the substance that is the working substance of this engine executes a cyclic path. What that means is that it is back to its original state at the end of one cycle. And since internal energy is a state function, it must come back to its original value. Therefore, delta U has to be 0 for the engine itself. And as a result, the first law of thermodynamics tells us that if you add together all the QIs, Q1, Q2, Q3, Qn plus 1 and so on, you are going to get the net heat flowing into the system, Q, and that is equal to delta U plus W in general, but since delta U has to be 0, this is the same as W. So the work done here is equal to the net heat going in. However, note the word net heat going in here. Not only is this net heat the sum of all the heats, but you have to also realize that some of these heat flows are positive and some of these heat flows are negative. In general, a heat engine will take heat from some reservoirs and reject heat to some other reservoirs. We are going to use heat flowing into the engine as a positive, this convention throughout, and therefore heat rejected will essentially be considered to be negative heat taken in. Now, what we do next is split up the total amount of heat going in, this net heat Q, into two pieces. The piece which is actually going in and the piece which is actually coming out. So, you define Q plus as a sum of all the Qj's, where Qj is actually positive. These are actually heats which are flowing into the system. And this by definition has to be a positive number. Similarly, Q minus is the sum for all Qk, where K runs over such reservoirs that Qk is negative. So all the heats being rejected are being added together. Of course, since Q minus is the sum of a lot of negative numbers, it's also going to be negative. And Q is the sum of both of these taken together. So Q is always given by Q plus plus Q minus. Note that in this convention, Q minus is a negative number. So Q plus plus Q minus is actually less than Q plus in size. Now, what we want to get out of a heat engine, of course, is the work. W is the output of the heat engine. Heat, of course, is what is the input. But here, note that the input really is not the entire heat Q, but the heat which is actually supplied to the system, Q plus. Only a part of that is actually converted into W, since Q is actually less than Q plus. The rest, Q minus, essentially is a waste, so to speak. So when we talk about the efficiency of the heat engine, we look at how much do we get as opposed to how much we put in. So the energy we get out of this is W. Energy we put in is Q plus. So efficiency eta is defined to be W by Q plus. And since W is the same as Q, hence the same as Q plus Q minus, we get this formula for the efficiency, which is often very useful in calculating the quantity. Eta, the efficiency, is 1 plus Q minus by Q plus. Let me point out once again that Q minus being negative, this quantity is actually less than 1. Now, as far as the first law is concerned, there is really no lower limit to Q minus, so it might seem like the efficiency eta, while being less than 1, can actually approach the value 1 in the limit Q minus goes to 0. At least, there is nothing in the first law of thermodynamics that tells us that such a thing cannot happen. However, as we will see later, this efficiency eta has an upper bound. It cannot really get even close to 1. So when we said that the second law actually says you can't even break even, you can see that in this formula. Eta, the amount of work you get per unit amount of heat supplied, cannot even get to the break-even point. W can never be equal to Q plus, it will always be less. And less by an amount depending on the temperatures of the reservoirs being used. We will see all that when we come to discussing the second law in a later lecture. In today's lecture, we will take a deeper look at some very simple heat engines. But before we do that, let me talk about a specific kind of heat engine which actually does quite the reverse of what a heat engine does. So far we have actually assumed that the heat engine somehow will take in heat from the surroundings, bunch of reservoirs, and convert a part of it at least into work. However, if this W were negative, we really have a cycle on which the external system is doing work, and what we end up doing is insisting that such a cyclic system be called not really a heat engine but a refrigerator. So that's just a matter of nomenclature. So a heat engine proper is one which takes in a positive amount of heat and converts it into work. A refrigerator, on the other hand, consists of a situation where the work done is negative. That is, work is actually done on the system and not by the system. Now, in this case, mod W, the magnitude of the work done, is really the input. It's the magnitude because we are really talking here about work being supplied to the system. That's the energy input. And the net heat extracted by the cycle, which is Q plus for the cycle, that is the output. So here what you are going to do is use the work done to extract heat from reservoirs. So Q plus is what you get out of it, and mod W is what you have to give to get that done. That's exactly what an ordinary household refrigerator does. It takes away heat from the inside at the expense of work being done on it in the form of the motor being run by the electrical circuit, and rejects actually a larger amount of heat to the external world. Now, coefficient of performance is an analog for efficiency in the case of a refrigerator. Note that here what we want to do is extract as much heat as possible from those places where you are taking heat, typically the colder places. And what you do in order to get that done is put in energy in the form of work. So coefficient of performance is defined in a very similar manner to the efficiency. Output as opposed to input, but here the output is Q plus and the input is magnitude of W. So Q plus by magnitude of W is defined to be the coefficient of performance. Now, one thing which many thermodynamics textbooks talk about is what is the relationship between the coefficient of performance of a heat engine and its efficiency. Frankly, such a thing cannot make sense at all. A heat engine has efficiency because it's converting net amount of heat into work. The coefficient of performance is essentially a property of a refrigerator, something for which amount of work done is negative. That being said, there are special situations where a heat engine can be run in reverse. Of course, if you're running a heat engine in reverse, the cycle is executing exactly the opposite path as it did before. All the Q's will change sign and all the W's will also change sign. So a heat engine which can be run in reverse actually has W which is negative, and therefore that is a refrigerator. When we connect the coefficient of performance of a heat engine with its efficiency, we are actually assuming that this heat engine can be run in reverse, and we are really comparing the efficiency that we will get when the heat engine is being run really like a heat engine, and the coefficient of performance we will get when we run the same thing in reverse and make it work like a refrigerator. Now, the reason why I am stressing this so much is that, as you will see during the course of these lectures, most heat engines, in fact almost every practical heat engine, cannot be run in reverse. So, strictly speaking, connecting the coefficient of performance and efficiency of a heat engine would be impossible, since typical heat engines cannot be run in reverse. That being said, for the ones which can be run in reverse, we can easily derive the relationship that I am alluding to. And for this, what we need to do is, first of all, start with a cycle which is reversible, something which can be run in reverse. We will have a lot more to say about this issue of reversibility in coming lectures. For the time being, let us just assume that a given heat engine can be done in reverse. And of course, in this case, we can use it both as a heat engine and a refrigerator. And when you are using it as a heat engine, let's use E as a suffix to the quantities there. So we will have eta E, the efficiency of the heat engine, and R will be used for the refrigerator part. So COP is COP of R. Now, when you run the engine in reverse and it becomes a refrigerator, the W for that, WR, is actually minus WE. So mod of WR, which goes in the denominator for the calculation of COP, is actually minus WE's magnitude. And since WE is positive, minus WE, of course, is negative, and its magnitude is exactly equal to WE. On the other hand, and this is where you have to be careful, Q plus R, which is total amount of heats added together for the refrigerator, which are positive, they actually come from those terms which give you Q minus for the engine. The heats that were rejected by the engine are now actually being taken in by the refrigerator version. So Q plus R is not the negative of Q plus E. The important thing to remember here is Q plus R is actually negative of Q minus E. What was heat rejected by the engine? That with a change of sign has become heat accepted or flowing into the refrigerator. Now with this, it's very easy to relate the two quantities. The coefficient of performance for the refrigerator is Q plus R divided by mod of WR. That's the definition. But since Q plus R is minus Q minus E, we can put that in here. And WR's magnitude is same as WE. So we have now expressed everything in terms of things related to the engine. And to relate this to the efficiency, all you have to do is get rid of the Q minus E simply by using the fact that Q plus E plus Q minus E is QE. That's the total heat absorbed by the engine, or WE. So minus Q minus E, this quantity sitting here, is actually Q plus E minus WE. You just have to bring the WE to this side and move the Q minus E to the other side. And then you end up with this expression, and dividing both the numerator and the denominator by Q plus E immediately gives me 1 minus eta E by eta E, or what is the same thing? 1 over eta E minus 1. Very often you will see a textbook say that the relationship between the coefficient of performance and efficiency of a heat engine is that COP is 1 by eta minus 1. But you have to remember that they are really referring to two different situations. One where you're running the heat engine as a heat engine, and the other where you're running it as a refrigerator. And that can be done only if the engine happens to be reversible, which frankly is very, very rare, but very, very important. With that out of the way, let us now take a look at some very special heat engines. We began by describing the most general possible heat engine, and of course it looked like a rather complicated thing, with lots and lots of reservoirs, maybe an infinite number of them, all interacting with a given cyclic system, which is actually doing work, maybe on many things, but we really had lumped them all together into one work source. Let us now take a look at the other extreme, the simplest possible heat engines that we can think about. So that's the theme right now. We are looking for the simplest engine, and note that an engine essentially interacts with a bunch of reservoirs and can have a work source or a work sink, something which it transfers energy to via work. Now the simplest thing that we can think about is one without any reservoirs at all. So of course in that case Q will be 0, and according to the first law, Q equals 0 obviously tells you that W is 0. But this will be something which is entirely self-contained, takes no heat from outside, does no work. And so, although it's consistent with the first law of thermodynamics, it's actually too trivial a thing for us to worry about. This is going to be of no use to us whatsoever. In general, anything in physics which does not interact with anything else, frankly, is as good as something which does not exist. So let's talk about the next level of complexity. Now what we could have, at least we could think of, are simple engines which have only one heat reservoir and only one point to which work can be transferred. So an engine like this, something which goes in a cycle, interacts with one reservoir and converts the entire heat entirely into work. Here W has to be equal to Q because this Q coming in from one reservoir is the entire heat coming into the engine, and since delta U is 0, W has to be the same as Q here. Now can such an engine exist? It would be great if it had, because this would allow us to convert heat entirely 100% into work. Indeed, such a thing would completely solve the entire energy crisis of the world. Before we go any further, let me ask you to think about a very simple question. We all know that energy is conserved. If something is conserved, how can you at all have a crisis in that? We all have learned that energy cannot be created, cannot be destroyed, it can only change from one form to another. So if that is the case, where is the crisis? The answer lies in the fact that an engine of this kind, which takes a positive amount of Q from a reservoir and converts that into work, a positive amount of work, simply cannot exist. How do we know that it does not exist? Frankly, there is nothing in the first law which says that this cannot happen. However, a couple of centuries of experiments in various forms have convinced us that this kind of an engine, one which takes heat from one reservoir and converts that entirely into work while going in a cyclic process, does not exist. We will come back to this issue later when we talk about the second law, but at this point let me just tell you that this is one of the ways of stating the second law, the fact that this engine cannot exist. Or equivalently stating that the reverse engine, one in which the work were going in, that is W were negative and Q also were negative, so heat was going out, something which converts work 100% into heat very much exists. In fact, all you have to do is rub your hands together. You don't even need a system going in a cycle in between. Just rub your hands together and you are going to be able to convert work 100% into heat. What we are saying here is that process is irreversible. Once again, we have not really talked formally about reversibility or irreversibility at this stage. We will discuss this at length later. For the time being, all we need to worry about is that the simplest possible engine we can think about, one reservoir and one point at which it can do work, simply cannot exist. Well, neither can the other simplest kind that you can think about. A cycle which runs between two reservoirs and does no work at all. So in this case, of course, Q1 plus Q2 would have to be 0. And we have taken T1, the temperature of this reservoir, the first one, to be higher than T2. In such a situation, it's obvious that Q1 greater than 0 and Q2 less than 0, Q2 of course has to be negative Q1, can very well occur. You don't even need an engine for that. You just put two bodies, two reservoirs, one at a higher temperature, another at a lower temperature in thermal contact with each other, and you are going to get a heat flow, spontaneous heat flow from the hotter body to the colder body. That of course is something for which we don't even need an engine. What would be lovely is if we had an engine which could do the reverse, that is take heat, a positive amount of heat Q2 from the colder body and reject Q1, which is now negative, to the hotter body. That is, run this engine in reverse. That way we could have a refrigerator which would not charge us anything for the electricity. Unfortunately, as you may have guessed, this kind of an engine also cannot be made. This is not a new kind of statement that we are making now. This is another version of the second law. Again, this is something we are not going to discuss until we talk about a practical kind of engine in some detail in the next lecture. So for the time being, just take it as a piece of information that the simplest kind of non-trivial engines you could think about, one reservoir from which it could take heat and one place to do work, and the other one, an engine which could actually run as a refrigerator, an ideal refrigerator, taking heat away from a cold body and putting it into a hot body without having to do any external work. Neither of these two very nice engines actually exist. So the simplest kind of engine that we can think about, which actually exists, is the following. One which interacts with two reservoirs, goes in a cycle in between them, takes Q1 amount of heat from one. Maybe we can call this Q plus simply because there's only one which is positive, and a negative heat taken from the other reservoir and converts it to do work. And this W of course is Q plus Q minus, and the eta for this engine is of course always 1 plus Q minus by Q plus. This is not a new formula, it's just that here there is only one place at which you are getting heat and another place to which you are rejecting it. So Q plus and Q minus here are not sums of many terms, just individual terms in themselves. Now a special kind of such an engine, one which can actually be run in reverse, which is why it's so special, is going to be our main topic in the next lecture. This is the famous Carnot cycle. We will come back with a description of the Carnot cycle and detailed calculations for various working systems soon. We will later on see that the Carnot cycle is extremely important, not only because it is so simple, but because it leads to many important theoretical considerations involving the second law. But all that is for later. Let me sign off here today.